Okay, so I just want to welcome you all back after lunch and thank you for joining us again. Thank you to this morning's speakers as well. Thanks, Scott, and thanks, Selma. We really enjoyed your talks. So my name's Allison Reynolds. I'm a lecturer in the School of Veterinary Medicine. I have had the pleasure of working with Cresset for a number of years, and I would recommend it to any biologist to get in touch with the chemists. It expands out your project and can give you kind of new dimensions and a new focus. So I would thoroughly recommend it. I hope chemists feel the same after today as well, so that they want to interact with us biologists as well. So I just wanted to introduce you first to Kev Lewison.
Yes.
Kev completed his PhD in computational medicinal chemistry at the University of Nottingham. He worked on the design and synthesis of selective ligands in GPCRs and computational method development for enhanced sampling methods. So you joined Cresset just last year, I think, as a postdoctoral researcher, and you've deepened your knowledge of computational chemistry in an industrial setting. And now he's here giving us a talk. Thanks, Kev.
Oh, thank you. Can you guys hear me?
Yeah.
Good. Okay, so I don't have to stand in front of the mics. Yes. So thank you again for the introduction. I'm Kev, and I'm currently a postdoctoral scientist at Cresset, along with my colleague Scott. And I'm here to basically bridge all of what you've heard this morning together to give you a bit of a package as to what you can now do now that you've gotten you started with your proteins. So yeah, you started your proteins, you got your ligands. So if you can imagine from Rob,
Can you share your screen, please?
it's actually not shared. Oh, no. Okay, sorry.
My fault.
Oh, you're right.
They need to. Okay, so. Okay, sorry about that.
No, you're right.
Good.
Okay. Did they hear me?
Yes.
Okay, they heard me. Okay, fine. So first slide. So I'm just going to bring it back to what you will have known now since your talks this morning. So with your talk with Rob, you would have learned some really fundamental principles of molecular modeling and computational chemistry in general. Through Scott, you'd have learned about happy and sad proteins and the protein energy landscape. And with Selma, you will now be confident with, the role of ligands, how you can start with a ligand search, or what you can do with your ligands if you want to change it up a bit, get some different ligands. So most of my talk is going to be on the assumption that you have a happy protein. So your protein is happy, and you're happy with the ligand you've gotten so far. So let's see what the first thing we'll talk about is. So Scott talked about crystal structure earlier on, and rightfully so. X-ray crystallography shows you one part of the picture. It's nice because you crystallize your system, you whack it into an XRD, and you just bung a laser through it, scatters, and you're basically told exactly where everything is at any one time. And if you have a ligand in there, you can actually see the different interactions that the ligand is eliciting with the protein. So in this example, you're going to see these green lines. Some of them are, so they're all showing you some sort of hydrogen bond of some sort. And it's also telling you the distance. So you can actually see how far away your ligand is sitting from a particular part of a residue and exactly what conformation it's in. So this is where we say, so this is a happy ligand. So the ligand is sat in, presumably, its lowest energy state. And in its lowest energy state, with the protein's lowest energy state, it's eliciting these interactions. And that could tell you a lot about, so if there was a ligand that you know a lot about, so in the case of any crystal structure in any protein, any ligand in a protein crystallized, you can basically see how the ligand is sitting in there, what interactions it's eliciting. And to be honest, the depth that the picture that this can tell actually gets quite deep. So I know a lot of you are biologists. Have any of you guys done knockouts before? Knockouts, yeah. So for me, I've never done a knockout, but for my systems, I had colleagues who did knockouts for me. So I was able to know exactly which residues were critical in eliciting a response. So for those of you who don't know what a knockout is, you're basically changing residues as you go along. Basically, for example, you might have an aspartic acid and you swap that out for I don't know, an alanine or something. And you're looking to see if the response that you're looking for in your protein is still happening, even if the residue isn't there. So, but I know a lot of you probably know that already. So you can look at these and say, okay, I know, okay, so these interactions are happening. Are they important? You might know if they're important. You might not yet. But these are the kinds of things you can tell from a protein crystal structure. So, okay, let's say you've listened to Selma's talk, you've done a bit of Spark, you've changed your ligand up a bit, you've gotten something nice in there, you've changed the fragment, but it's not in a crystal structure. Now, of course, if you want to see exactly how your ligand is going to sit inside your target, you're going to need to put it in there. How would you put it in there? So Scott earlier on talked about docking. That is very common, you know. And there are two sort of go-to methods for when you're trying to get your new novel ligand into a protein. So the first thing you could do, if you have a ligand in your protein, is align it. And I could ask any of you guys how that would work. I guess you guys could tell me. You could just do a substructure alignment. You could just look at similar components of your reference ligand, basically slap your ligand on top of it and basically look at how it sits. Or if there is no ligand in your pocket, you've removed it, or you're not too interested in the reference, you just want to have a look and see how you get on, you can perform a docking experiment. So basically what you're doing there is you define a binding pocket and you let the method conformationally sample your ligand to find, again, a happy state and put it into your happy protein, assuming your protein is happy, because of course, all of this, I'm assuming you've prepped your protein and it's relatively happy. It might not be, but hopefully it is. So I'm going to get into a bit more about a lot more deeper things you can look at now. Now that you've got your protein, you've got your new ligand sat in your binding pocket, what can you do now? So as I've said before, and as I'm aware, a lot of you have done biological assays. I've seen some posters, there's all sorts of assays in there. So you guys know about biological data when it comes to your ligands. And, there are different types of assays you can do. So some of the ones I'm familiar with, especially, is stuff like binding affinity. I've done a lot of work with kinetics. And this kind of information you can then bring forward into your computational analysis to predict how your untested ligands might behave. So SAR is structure-activity relationships. Now, you guys probably already know that too. But to computationally model how your new happy ligand and your happy protein might behave, you're going to need to have data. Data is good. A lot of data is really good. And with more data, you have more choice. So I've made a little, I think it's a Boston Consulting graph. Rob helped me out with that. And basically, I'm telling you here the kinds of analysis you could do with different quality of the data and the amount of the data. So if you have quite a low amount of data and also it's not that great, you could just look at your protein and look at your ligand and how it's interacting. And as we said, so some of the very on the surface investigations, so things like interactions, distances, the conformation, look at the torsions, just have a look. But of course, you would probably need to know what's going on there to make sense of that. If you have a lot of high quality data, but not too much, you could do an activity atlas. So that's a qualitative analysis. You can look at components of your ligand that your happy protein likes. And if your happy protein likes these parts, it will tell you, and it will tell you if it doesn't. But there's different types of metrics you can use. We call it activity cliffs. I'll cover that in a bit. If you have a lot of data and it's very good, you could do anything you want. You could do anything on this and some. So basically in this top right corner, you could do 3D QSAR. So that's basically, you could do a quantitative SAR, or you can do relative FEP. So FEP is going to bring back some fundamentals that Rob mentioned this morning. And hopefully you can piece the puzzle together. And also if you have a lot of data, but it's not that great, you can run a regression. I'm sure all of you know what regression is. But for those of you who don't, it's a line on a graph in the simplest way possible. So sometimes you have this data and you don't really know what SAR to do. So you just have a look. So this is just, you don't even have to memorize this. This is just an example thought process I might go through before I run a structure activity relationship experiment. I might think about, am I going to use a docked pose? Am I just going to align it all? Do all of mine. So of course, in all of our methods, you have to, you don't have to, you could be a bit rebellious, but ideally you'd align your new ligands to a reference. So, they're all, so they're all superimposed on top of each other, to give yourself all of the ligands in the binding pocket, superimposed. And you can decide from that point, what is going to help me. Am I trying to predict an activity? So for example, am I trying to predict an IC50? Am I just trying to see which parts of my ligand my protein likes and doesn't like? And again, depending on what you're looking for, you could do different types of analysis. So for quantitative SAR, I split these into two categories, mainly. You can do a regression model, as I touched upon before, but also you can do classification models. And obviously, classification models, you're putting your ligands into classes. You're basically saying, you are in this box, you are in this box. How do you get to that box? Sometimes if you can think about a decision tree, am I over 5? Am I over 5 foot? I mean, if you're over 5, you might be over 5 and not over 5 foot. So you go over there, and if you are, you go over here, and then eventually you end up in a box. A regression, you plot your ligands by activity. So if you can imagine, you're plotting activity by maybe molecular weight, and you're able to create a regression line. And whenever you have a new ligand with a known molecular weight, you can add it to the graph, and it will predict how that ligand might behave based on its molecular weight. Of course, it doesn't have to be molecular weight. You might have other types of information that is useful. Sometimes, you might know from the literature, more hydrophobic components of the ligand, and you might want to do it with hydrophobicity against activity. It's in your hands. You literally can do whatever you want. So I want to build a regression model. How am I going to do this? I have at least 30 to 40 compounds. So I have a nice amount. They might be great, they might not be too great, but I have 40 compounds and I've aligned them, they're ready. And they're in the activity range of about 3 log units. So you're getting a nice sample range here. You're not looking at, just 1 log unit, or you're not looking at 2 compounds. I mean, if you're looking at 2 compounds and get the line through the 2, you're not sampling very well. And the activity values are evenly distributed. That is quite an important thing to do as well. And of course, we talked about this before, align your ligands, have them all in the same environment, and we'll compare them that way. Because of course, you probably wouldn't work too well if you had 1 ligand in the binding pocket and 1 just floating in solvent. I mean, that doesn't tell you too much. And here's one I did earlier. So here's some ligands that I've aligned. I know the activity of all of these ligands, and I've aligned them. They're all superimposed, and I've basically said, hey, I want to see, based on I've given you these ligands, the activity, my known activity, I'm basically going to train my model based on the known activity and see if it can tell me basically if it can tell me how it thought these would predict, it would perform, sort of like not knowing anything else. So, okay, this is how they did perform. Go off, see if you can get like common patterns and whatnot, and tell me if how they actually behaved is how you think they behaved. And here we have a line, your regression line. And all of these points represent ligands. They're all in there. You can't see them all there, but you can see them all here. And if you can imagine, you have a new ligand, it will just be a new point. So your new ligand that maybe had an activity of 8, great. The model, based on this line, could place it, anywhere in here. But again, based on the components of the ligand, it will be able to tell you whereabouts it thinks it would behave. And if you don't know the activity, so let's say you did the biological assay. The software doesn't know the results of the biological assay. You can basically just use it to see if it would have predicted what the actual biological assay gave. And what do I need to build a classification model? So let's say I have the same data set. I have the same 40 compounds. But this time I have 2 categories. I'm just going to use a random example. Let's say I have good and bad. And I've basically, it would basically come up with a reason as to why to classify these ligands into good and bad. This is just out of the park. Just, is it good, is it bad? And you go down the decision tree, if you think of it like that, until it gives you where it thinks these ligands would land. So if you can look at all of that. So on the right here, we have some confusion matrix. Some of you might be familiar with this. It's placing my ligand into boxes. So you're not looking at an exact value, you're looking at a quality, almost, it's still a quantity, but you're looking at whether it fits a certain criteria rather than whether or not you can, so if it can give me the exact value. And of course, this could also be very useful as well. Yeah, if you're trying to look for ligands that might be, I don't know, just high log P or whatever, and you're trying to filter all of those ligands out. So qualitative SAR, I mentioned earlier on, I'm going to go into a little bit more detail about now. The picture on the left looks very cluttered, but it's cluttered for a reason. So for all the talks this morning, you've seen this similar pattern. You've had basically a ligand in a protein. These colors here are basically telling me different things about the properties of the ligand. And if you can imagine some of the colors, so this purple color, I'll go into this into a bit more detail, but the purple and the green colors are telling me whether or not these regions are ideal hydrophobic interactions or not ideal hydrophobic interactions. So you're not looking at activity anymore. You're looking at some stuff like electrostatics. You're looking at clashes. You're looking at, as I said before, hydrophobicity, and you're looking at more qualitative aspects of the ligands. And activity minor, you could start looking at different components of ligands. So basically how changing components of the ligand impacts certain characteristics of it. So again, you're not looking at a particular activity anymore. You're looking at parts of a ligand that are changing the overall ligand or the overall ligand profile. And both can be very useful. So here's an example case of qualitative SAR. So let's say I did this earlier. And you can see in green, we have an activity cliff of favorable hydrophobics, and in purple, we have unfavorable hydrophobics. This model is basically telling me that these regions are unfavorable in the sense of hydrophobicity, and these green areas are favorable. So basically, these areas are happy where they are, and these areas could be a bit better. They're just they're not eliciting the sort of optimal hydrophobic interactions. And again, that could be very useful if you don't know which part of your ligand is doing something and you want to improve your ligand. You can look at a component of the ligand and go off and change that. You could say, okay, I know this part of the ligand, it's not ideal hydrophobically. Let's give that a change, just make it into a more hydrophobic group, or so on and so forth. It's electrostatics. You could literally any characteristic you can modify based on these qualitative characteristics. So that was SAR. So, looking at properties of the ligand in your analysis for predicting how new ligands work. But as you heard, it's like a general theme through today, molecular dynamics, which is, in a nutshell, again, just snapshots of a system over time. And MD simulations are, they're very useful, and they serve many purposes. But on the surface, if you can remember what Scott was saying about an energy landscape, if you can simulate the protein, so if you can imagine in your X-ray crystallography, you've got your protein in state X, you can, in a very colloquial way, let your protein wiggle about and basically see how energetically it changes over time. So, you might notice your protein swinging into favorable states, unfavorable states. You might find that it remains in a favorable state for longer and doesn't stay in unfavorable states for as long. Little sort of on the surface things. And you can also see how interactions change over time too. You can see bond distances, torsions, again, all principles you would have heard of from the earlier talks. And that's very useful for knowing how your protein is interacting with how your ligand is interacting with your protein over time. So here's an example of a jiggling system. So this is a electrodynamics simulation that I've conjured up. It isn't actually mine, someone else conjured it up. But if you can imagine now, the purple system that you see that appears mid-simulation, that's your reference structure. That's your starting structure. So of course in MD, you start from point A and you end at arbitrary point B. I mean, you can run it for as long as you want, but purple is point A. it's agreed. That's where we started the simulation. And the green or blue, I get greens and blues mixed up, but the other one that's not purple is your simulation. You're seeing it change with respect to the starting position, and you're able to see even the ligands moving. And in these intricate movements, the interactions between the ligand and the protein, these are all changing over time too. And as a result, your energetics profile, your energy landscape is changing, and you're basically sampling your protein ligand interaction over time, which can give you a bigger picture of your system. So MD simulations, of course, as I've mentioned before, in the middle here, you can do atom distances. That's quite a basic thing to do. You just click atom A, atom B, tell me how far they are and how far do they get from each other in a simulation? What's the furthest distance it gets? I mean, does it break? Does it detach? You can see things like this from by eye or by measuring it. RMSD, so if you remember what was just on the screen with the blue and the purple system, you see that the blue system is deviating from the starting position. So you have your point at 0 time and 0 RMSD, because of course, system A is the same as system A, because that's where it started. But as it moves, you can see that as a system, it's deviating from its starting position. And you can see how much your system deviates from its starting position. And potential energy, as Scott's mentioned quite extensively earlier on, you can see the energy profile of your protein. This is quite you're seeing here, I mean, by eye, it's quite constant. You're not seeing anything unusual in this example. I mean, if you had for example, a protein unfolding, you might notice a spike in energy while it's breaking that interaction that's unfolding the protein. But in this situation that I've showed you here, there's no real change. The system is just existing. It's just moving, and the energy profile is changing ever so slightly. So why is that useful to know? Well, of course, as I said in the example of an unfolding protein, RMSD wise, even if you didn't view your molecular dynamics in this sort of representation and you just looked at that, if you saw really large changes, that almost irreversible changes, you could tell from that number that, yeah, okay, the system has deviated quite far from my starting position without even having to see it deviate. You just know from the number it's deviated very far from starting position A. And yeah, these are very powerful analysis tools you could use. But you could take it further. So you thought that was complicated. It gets more complicated. And I'm bringing it back to the fundamental that Rob talked about this morning, thermodynamics and stuff. And the really, really nice example that both Scott and Rob mentioned earlier on is the captain in the ship. I love that example. So if you can imagine this star is your captain. So okay, we're trying to measure what is the energy of my starfish. So my ideal star. So this is the starfish I want to know. How tightly is this starfish binding to my host? But as Rob said, it's very difficult to just take the boat away from the sailor and measure the sailor computationally. That's very difficult to do. So what I could do is I can start from a different starfish and slowly but surely change my starfish into my starfish of interest. So start with a different starfish, slowly change it into the starfish of interest, and measure relatively the change in energy. And that way you can generate a relative free energy from just changing. And as you can imagine, by changing the ligand, you're also changing the interactions between the ligand and the protein, and also the ligand alone. So the free ligands obviously differ in energy, and the ligands in the host are going to differ in energy. And you're seeing the change in energy by basically putting my starting starfish, so having my starting starfish free, put it in my host, and having my starfish of interest free, putting it in my host, and seeing how they differ, and getting a free energy that way, relatively. And enhanced sampling doesn't stop there. FEP is a well-used one. Well, it's very well known now in the computational space. But there are other things you could do. You might have a huge system, several 100,000 atoms, and computationally is quite demanding, but you're not too interested in the intricate interactions of your protein. You can coarse grain it. So what you can do is you can represent a family, like clusters of atoms, as beads. So if you can imagine, you have a bead that represents 4 of your atoms in your system. So you'll end up with less atoms because, of course, every 4 atoms is now being represented as 1 atom. So you basically have 4 times less atoms. And you can imagine how much quicker your calculations then go that way, because you're now looking at interactions between these, so atom groups rather than between individual atoms. So that's one way you can simulate systems for longer timescales. Again, there's different things you could do. You can look into your binding and unbinding, so you could force your starfish out, see how it comes out, and try to get and basically start with your starfish in, force it out, and have your starfish out, have those 2, A and B, and you can figure out how quickly your starfish comes out and how quickly it goes back in, and you can measure kinetics that way. So there's different things you can do with molecular dynamics. It's huge, potential is endless. But again, don't think about those too much. Those are those are very particular problems. But again, it's just to show you the possibilities that this technique can bring to you. So this is good because so are there any PC gamers here? PC gamers? No PC gamers. Who has time to game anyway? Basically, as I talked about earlier on, just before, a lot of these techniques are quite computationally intense. So we've gone from a time where we were running simulations for, very, very short timescales. And as the computational hardware improves, as gamers want to play, games in 4K and stuff like that, we're getting really good hardware that scientists piggyback off. So if you can imagine, not very long ago, we started on simulations, very short simulations, quite simple systems. And now we're modeling quite large, complex systems for longer timescales. And by doing that, we're able to gather more data. We're able to learn more things about our system that we wouldn't have been able to do before. So I guess in this slide, it's a thank you to the gamers, because people enjoy gaming. Sometimes we just enjoy simulating, and we can now do that while they're gaming. So it's a symbiotic relationship. I love it. And yeah, so hopefully you can kind of see not only the evolution, so yeah, that you can sort of see how we started from place A and why we're able to do what we're doing today and all of the things we talked about today, but also hopefully you'll have a bit of an idea of the methodologies that you can use and how powerful molecular dynamics can be for your experiments. So to wrap up, hopefully after my talk, I'm confident. I'm seeing faces. I'm confident after my talk, you have an idea of the kinds of information you can get from structural data. So you'll be able to know that, I can see my ligand in my protein, I can see where they're interacting, I can see the types of interactions, is it pi stacking, how is my ligand interacting with my protein? Now that if you can make a brand new ligand, slot it into your protein computationally, you'll know now that you can use the known biological data and even just the structural data of your ligand to predict the behavior and properties of your brand new ligand. You'll know now that MD can be used to sample protein ligand interactions over time. And you'll know now that conformational changes over time can be further sampled to gain deeper insight into your protein ligand system. So hopefully I haven't frazzled your brains too much. I know there was a lot to cover in there, and I know how it sounds on the surface, but this is just an idea of the types of stuff you can do with these methodologies. So thank you everyone for listening, and I'm happy to take any questions.
Thank you very much, Kev. That was really interesting. I think I'm going to remember your jiggling molecules for a long time now. So can I just ask whether anyone in the audience has any questions here?
Yeah. Hi, Kev. Great presentation, and thanks for the picture of your home getting DC set up. Can I ask, just for the MD, could you comment at all on more difficult systems like transmembrane proteins and how you might go about simulating them? Yeah,
so very good question. So transmembrane proteins, again, so if you can imagine, a lot of the systems we've talked about, enzymes and soluble proteins, you can simulate your protein in water. They dissolve, and you're basically just viewing your protein and its behavior in a soluble environment, in your water environment. But Morgan's right. With a membrane protein, you have a membrane. And now with this membrane, you're also modeling so not only are you modeling the protein in the solvent, you're modeling the protein in the membrane in the solvent, which adds a layer of complexity that it's quite adept, but it's possible. You know, we do this. This is something that we do quite routinely now, as it's becoming more, it's easier to now, as I was talking before, simulate systems with large numbers of atoms. So yeah, that is a very important thing to do, and it gets done. Yeah, no problem.
Right. Post-translational applications, things like phosphorylation or methylation.
So theoretically, anything's possible, but but that's a good question, because again, processes like this, and I mentioned before the example of protein folding. These kinds of processes tend to take they tend to happen over quite long time spans. And Scott and I were talking outside about, you know, the problems that we call them, okay, a protein unfolding, a rare event. It's hard to basically see a rare event when you run a linear simulation. But enhanced sampling, there are ways that you can measure these things. So for example, what I was talking about before about measuring kinetics, these phosphorylation events, it depends on what you're looking for. If you're trying to look for, you know, the energy change of that phosphorylate, that event, you can basically start from your phosphorylated and your basically with the phosphorus gone, and you can go back and forwards from those two points statistically. So again, I didn't mention anything like this, but you're going that statistical mechanics way, and you can basically sample that event in a more sort of focused way to gain more insight. So yeah, these quite complex sort of processes can be modeled, but it takes a lot of thought, a lot of resources, and yeah, it's very time consuming, as you can imagine.
I think we have a question just from online, right?
Yes, we do have one. Apologies, I'll try and read this as best I can. If the activity data is given as an application rate, say data like 78% control at 1 part million rate, not like the common IC50, does this set of data allow Flare to model the QSAR?
Okay, that's a good question. So
well, for my data, we didn't have IC50 actually for most of the compounds as well. So we actually used biological activity. That was, it was quite crude. We just measured the number of blood vessels in the spine, along the spine of a zebrafish. And that's, I suppose, the only limitation with that is, you know, you're kind of, we were limited between 0 and 30 in terms of numbers. Yeah. But I do think, sorry.
No, it's
from a biological perspective.
Yeah, it shows that, yeah, it's common that people don't have, you know, just a number. But of course, even with the IC50s, what you would have seen there is a logarithmically derived number. So you can model it that way, but you tend to have a value that represents your value. So percentages, I can't see why that isn't possible. I can see, you know, the parts, yeah, I can see as long as what you're measuring is quantitative, you can use quantitative SAR to predict the activity. So I'd say it's possible.
People tend to go to qualitative measures or categorical measures quite quickly on that, because the error bars are quite big generally. Yeah. Which isn't necessarily true, right? So if you do sort of N of 20 and you can actually have good statistics, but you tend not to be in that space. If all you've got is a parts per million or a single shot inhibition, you tend not to have lots of repeats. And so given that you've got big error bars, you might as well go to not a quantitative measure straight away. You might as well try and build a classifier and say, is this active, is this not active, or is it yes, no, sort of? And then just, you know, that'll get you started. And then you might then think about building more quantitative predictive models on the back of that, but only if you generate enough data. So it's all sort of data points.
Do you want to summarize that for the people online?
Okay, yeah, so for the people online, what we're saying was, if you have a complex situation like this, you might want to start out doing a classification rather than trying to predict your value quantitatively. So you might want to start with, is my molecule active or is my molecule not active, and work your way from there.
Very much. That's great.
Thank you. Thank you very much. Thank you very much, everyone.
Okay, the next speaker is actually joining us online, so we're just going to need to set that up now. So I think I just need to make him a co-host. Is that correct?
He is.
He's there.
Yes, so Colin is online as a panelist.
Okay.
You should be able to share the screen.
No, I can't.
He can't
Host has disabled participant screen sharing, it says.
Okay, well, that might be. I'll make you a co-host, Colin. There, you see if that helps.
Share my video either. I don't know if that's really that important.
Okay, I'm just going to stop sharing. Just give me 1 second, and then.
Right, I think it's working now.
Yes, Colin, I just gave you the word, so you should be able to share.
There we go.
Okay, that's great.
Let's get rid of that.
Do you want to see if you can put that into presenter view? Just we can see it kind of.
Oh,
Yeah,
okay.
perfect. That's perfect. That's actually working now. Okay, I'll just give you a brief introduction then, Colin, and then I'm just going to turn off the microphones here just so that your sound comes through. Okay, can everyone hear him? Okay. Yeah. Okay, that's great. So just to say thank you very much to Colin. Well, thank you very much to Kev. That was a great talk. And some great questions as well. So clearly people are listening. So, so just Colin is going to talk to us about just a life in a day of a computational chemist. So Colin studied chemistry at the University of St. Andrews, and then in his final year as his project, he was introduced to quantum mechanics calculations by his future supervisor, Colin Thompson. So he did a PhD just on theoretical studies of enzyme inhibitors applied to cancer research. And he said he's since worked out that the 3 years of calculations he did for his PhD could be done in under an hour because computers have increased in their speed by over 1 million times in that time. So just making us all feel relevant now. But not many people could probably do it the way you did it anyhow. So Colin immediately started to work as a computational chemist with Beecham Pharmaceuticals, and he spent his whole year working for Beecham's, working for SmithKline Beecham's, and then subsequently GlaxoSmithKline. And he retired from Big Pharma last year and is now working as a consultant. And he has been applying his computational chemistry methods to kind of all phases of drug discovery and drug development, from the initial target validation right through to manufacturing support. So Colin, we're really looking forward to hearing your talk, and I'll let you start then. Thank you very much.
Thank you. I'll go straight on to the first slide. You can see the right presentation mode, can't you? Because I can use...
There's a brief personal history. Yeah, is that correct? Yeah.
Yeah. Okay. Great. Yes. So thanks, Alison. You've just done this timeline here. This is when I started studying chemistry, and I got bitten by the bug of doing calculations in the final year of my degree. As I said, I even got a paper out of that, which was quite nice at the time. And as Alison said, yeah, computers got so fast now. Actually, I recalculated it, and my PhD, my 3 years of PhD, can now be done in 100 seconds. So you can make your own mind about whether that's relevant still or not. I've worked on quite a few different drugs over the years. Ones that we know the target of, for instance, the penicillins, where we knew the penicillin binding protein and beta-lactamases that were the targets, and things like this glitazone here, Avandia, where we didn't know the targets at the time. So I've done both ligand-based and structure-based work. This is a rough timeline of the kinds of things I've done, and I've worked on many different areas. So AV is antiviral, OB is obesity, antibacterial, mimetic. That's depression, anxiety, that's Parkinson's disease, antiviral again, COPD and asthma, AIDS, and even H2 ulcer work. It's been, this is more or less chronological. I did work early on mostly antiviral and antibacterials. Then there was a barren management period in the middle when I was running the group and telling other people what to do. And then more recently, I've been working on development compounds. I want to tell you something about that, and even supporting manufacturing. So first of all, what is a computational chemist and what is computational chemistry? Well, I've used a very broad definition of computational chemistry, and that's something you do on a computer that progresses chemistry. So that's not PowerPoint like this or ChemDraw. Those are valuable communication tools, but they're not actually progressing anything. The problem is that it's quite tenuous, really. If you think about it, computational chemists just produce ideas and opinions. Very few of them go into the lab and make the compounds. Some computational chemists have budgets to buy things, but very few test them as well. So really, a computational chemist is an ideas merchant who has to be an influencer. You have to actually convince other people to do something, otherwise you're not very good. Computational chemistry can be used at pretty much every stage in drug discovery and development. I've worked on most of these areas now, right the way through from target identification in the first place, where you are trying to identify usually a protein. It doesn't have to be, it could be RNA or DNA, but usually a protein that you're interested in. So things like bioinformatics, structural analysis, construct design is an important one that most people don't think of. If you just trust a molecular biologist to produce assay material, reagents, and if the wild type protein at full length doesn't work, they'll start chopping down from the N terminus and C terminus until they get better behaved protein. You really should get the computational chemists involved at that stage, particularly if there's structures, because we don't want to be severing halfway through an alpha helix or a bit of beta sheet. So contract design is quite important. Screening is important, and this is an area where computational chemistry has a big impact in pharma, because you never have enough hits. And compound rescue, where you identify false negatives and rescreen them, is a very, very powerful technique for getting more leads. You've heard a lot about lead optimization already in terms of ligand-based design, structure-based design, so I won't talk much about that. I'll talk a little bit about molecule generation and model building, but I also wanted to talk a bit more about after discovery, when you go into development. Traditionally, this is where computational chemistry stops, but it needn't do so, and I don't think it should, particularly these days. The computers are fast enough so that you can actually do quite influential work and actually have influence over millions of pounds worth of material. So I will tell you something about that. So let's start with the first one. So screening support. Now, the problem with screening, high throughput screening this is that the quality is often not that high, because the emphasis has been for years, since the mid-90s when this started, high throughput screening, on pennies per well. You know, how much can you do, how quickly and how cheaply? And if you're interested in quantity, then quality often goes out the window. And you can get situations like this. This is an average of the activity over 20,000 plates in one particular screen. And you can see you've got a pattern. You're more likely to find active compounds in the middle than you are on the outside. You've got edge effects. You see this kind of thing, and it could be due to evaporation. It could be due to dispensation errors. You sometimes see striping where one particular row or column has less activity. And again, that can be due to the robotics. And there are simple ways that cheminformatics, that you can actually adjust these and rescue some of the compounds around the outside and progress those. And this is something that computational chemists do routinely, but it has a big impact on chemistry further down the line, because if you don't find the hit in the first place, you're never going to actually do any SAR around it. You can also look at more than one screen and do things like identify nuisance compounds, compounds which interfere with multiple screens. For instance, highly colored compounds or fluorescent compounds are not much use if you're using a fluorescent assay readout. And then you get things, panactives. Some of the molecules you often see in papers in literature, things like chromones, coumarins, those sort of things, flavones. They are panactives because they happen to have a lot of hydroxyl decoration on them, and they are often chelators of metals. So if you've got a metalloenzyme that you're looking at, or even if you've got metal impurities in your screen, you can get these odd effects with these kinds of compounds. So you really want to be careful with those, but you can't just count them. Frequent hitters can actually be frequent for a reason. We thought some years ago we had a series of isoindolines that kept coming up in different assays, and we thought, well, these must be nuisance compounds, until we went back and did what we should have done in the first place and counted them. And we found that actually there were a large proportion of the screening deck. There were about 1 or 2% of the screening deck was just this one chemotype. And it turned out it was an enormous combinatorial chemistry library from the mid-90s that all of it had been shoved into the screening collection, probably so that someone could get their end of year bonus, I suppose, on numbers. And in actual fact, they weren't frequent hitters. They were actually hitting below average, and they were genuine hits. It's just there were so many of them that they turned up more than you might expect. Of course, that kind of thing would be addressed if you design the screening collection correctly in the first place. And this is another thing where computational chemistry has a big impact. In fact, I really would recommend that all screening collections, rather than compound collections, screening collections should be owned by the computational chemistry group, seeing as they have all the skills to design a good screening collection. Obviously, they can do the calculations or look at the assay data for properties like hydrophobicity and so on. They can remove all the things you don't want that we just talked about, reactive groups, fluorescence, things that get easily metabolized like esters. But this is the crux of it. How do you get a small but diverse collection relative to full collection? And this is where we at GSK came up with a couple of metrics, the pi and the alpha. So the pi is the probability a cluster contains a lead. So that's how good the particular cluster is at providing leads. And then this is the hit density within a cluster, the alpha. And if you, with some fairly simple mathematics, you can actually devise a screening collection which samples effectively from many, many different chemical clusters, and also within those clusters selects a certain number from each cluster in relation to how likely you are to find hits. Right, moving on through to hit to lead. As I said, you need as many hits as you can get because they fall out very quickly. They get NFI'd, no further interest, very quickly. And also to start with, you probably from your screening will only have one example or a couple of examples per chemical type. And traditionally what you would do is you would actually look for similar structures in your mains collection or things you could buy quickly. And you would make linear arrays. And this is where you would just change one functional group or a couple of functional groups, things like amides, reductive amination, Suzuki coupling, things you can do quickly and easily. And this is an example of the kind of thing that you wouldn't see, but I would advise you to do instead. And this is a sparse array. Traditionally, what you would do is you would take one of these R1 groups, say you focus in on number 10, and you would make as many R2s as you could. And you would take one R2, say number 20, and you would make as many R1s as you can. And that gives you 2 stripes through the chemical space. And if you're lucky and the SAR is additive, that will be enough for you to work out where the most potent molecules or the most desirable molecules are. If the SAR is not additive, then you really need something like this sparse array design, which samples efficiently through the space with the minimum number of molecules made. And again, this is obviously a computational chemistry approach. The other thing you can do is use data-driven approaches. This is an advantage of working in big pharma, is you have lots of data. And there's something called matched molecular pairs you might have heard of. What I've called them are historically successful changes. And this is where you look at all the molecules you've got in your collection where they're pairs which differ by one thing. So maybe you've got a phenyl group that gets changed to a hydroxyl in a whole series of different molecules. And you look at average what happens on that change. And it may be that you just get a bell-shaped curve and you get as many failures as you get successes. But often you get a skew to your distribution. For instance, if that was log P, if it was about hydrophobicity, and then you would expect on average, going from a phenyl ring to a hydroxyl, to get a more polar molecule, which is is more hydrophilic and less hydrophobic. And you can do that for activities and things like that. And what you end up with is a list of changes you can make to any molecule you see coming through that has a phenyl ring. You know to change it to a hydroxyl for certain things. You also come up with different, more sophisticated similarity metrics than just the daylight fingerprints everyone uses to actually do scaffold hopping as well. And what you end up with is an automated platform called a molecule generator, where you feed in molecules and it produces things which are similar to what's been made before, but in your particular chemical series. Now, these things have got a very bad reputation amongst synthetic chemists. They have a reputation for being providing things that are really difficult to make because there's too many chiral centers in them, making things which just fall to bits because they're not stable, or take too much in the way of synthesis. So we thought we'd test that, and this is a nice paper here, a Turing test of molecule generators. This first bit has been done a few times before. I've seen about 3 or 4 papers where people compare the ranking that chemists do. And to summarize these papers, essentially a chemist over time agrees with himself or herself about 50% of the time, and they agree with each other about a quarter of the time. And that's what we've done here. We've taken 4 different molecules and asked a bunch of chemists to come up with 20 new ideas based on those molecules. So that gives 80 ideas per chemist. Then if you look at this matrix, you can see that these are the ones where they completely agree with each other. They've drawn the same molecule, in other words. And you can see that about a quarter of the time, 20 to 30 out of 80, they have the same molecules. And that's good because you do want some sort of consistency there and some sort of basis. This second bit is less usual. This is when we've compared the molecule generators' ideas to the chemist's ideas. So we've taken a random selection from these chemist ideas up here, and we've seeded them with 75 computer-generated ones and asked the chemists to score them. And these are the results. Now, if these were all rubbish, the computer-generated ones, then the scores would be down here, 20 or 10%, depending on whether they like their own ideas or not. But you can see the ideas are up in the 60 to 80 range, and that's for different targets and across a whole range of different chemists. So what we can see from this is that this has passed the Turing test, and the computer-generated ideas are indistinguishable from the chemist's own ideas. So that's quite good. A little bit about lead optimization. Now, I'll try to keep this fairly brief because I know you've heard a lot about this kind of thing before. I'm focusing here on models rather than structure-based and ligand-based design. Big Pharma has a data advantage here as well, because we've been running the same assays over and over again for thousands of molecules, particularly phys-chem like log D, log P, and liabilities like HERG, which is a heart ion channel that you don't want to hit, and cytochrome P450s, which are detoxification enzymes, which you also don't want to inhibit because they metabolize and eliminate some drugs, and you get drug-drug interactions if you inhibit these things. The models for those are pretty good, unless you're working in some very esoteric area of chemistry, you know, boron chemistry or something like that, then the models are pretty good. Unfortunately, the affinity models, you've only got 20, 30, 40 data points from the molecules you've discovered so far. So the models are quite poor. And don't let anyone tell you that machine learning is the savior here. Unfortunately, artificial intelligence, machine learning models, in my experience, do not extrapolate well. They're really, really good at memorizing data and interpolating. They will find the best troughs and hills in your mountain range that you've looked at through already. So they're very good for filling in existing data, but they won't take you from where you are to a better place. And what we would do in this case is we would take something simpler. We would take a physics-based model, in fact, that Kevin was just talking about. You'd use something like free energy perturbation, which has got some predictive power to it. If you start off with molecules, micromolar molecules, which are PIC50 of 6 to 7, it will predict things which are 8 and 9. And if you test them, you'll find that some of them actually are 7.5, 8 in PIC50. You then take those results, build the models again. You also do something called active learning, where you identify parts of the chemistry space where the model is poor and not very predictive, and you make more molecules there as well. So you're not just making molecules which you hope are going to be better, you're making molecules to help the model. And then you keep going round and round and round until you get your candidate. And normally that's where computational chemistry would end. You've got your development compound, that's it. Some more far-sighted companies, such as Pfizer, have actually put a lot of money into supporting development as well. And this is a different area. Instead of having instead of having thousands of molecules which are really not important until they're a candidate, you've got one very high value molecule which is the candidate. Or actually, in actual fact, you've probably got a few different salt forms of it that you were searching or comparing, but you haven't got that many molecules. Because you've only got a few number of molecules or even one molecule to work with, you can afford to do very expensive computational techniques. So you can afford to do quite expensive QM calculations and things that are coming up these days, crystal structure prediction, which takes a heroic amount of computational effort. You need to, first of all, you need to build a special molecular dynamics mechanics force field for the molecule that works not just in the gas phase, but also in the solid state. You then have to search through lots of different space groups to find the one that you want. And it's very expensive. But with things like Amazon Web Services now, where you can run these things in unfashionable times in the middle of the night, then you can actually do some of this crystal structure prediction fairly cheaply. You can do things like morphology, so you can predict the shape that crystals will be. You want a nice block shape in development because those things are easy to process and pour well. Needles do not pour, they jam up. If you've got plate crystals, they have a large, usually hydrophobic face, slow-growing face on the crystal, and they often stick together and agglomerate and gum up the works. You can look at things like hardness, elasticity. You can, if you've got any slip planes through the crystal that allow you to material easily, or whether it's going to be very hard. And polymorphs, which is related to crystal structure prediction, is an area where it's as well to have an opinion about what you've got when you're going through from candidate and do some kind of polymorph risk assessment. This is an example here of a UCB compound, retigotine. Now these red forms here, form 1, are the form that was developed from the candidate. And now I'd be worried about that straight away because it's got a very low density. 1.2 grams per cc is very low for an organic molecule. Even one that's got quite a lot of sp3 character in it and won't pack as well as sp2 and amides and so on, it's still worryingly low. And I would be saying at this point, can we find some more dense polymorphs? And unfortunately for UCB, they did find a more dense polymorph. I can't remember whether they were still in development or whether actually in manufacturing at that point, but they found a new form, and this new form is not only more dense, you can see it's also more stable. The lattice energy is much larger. This means it's less bioavailable because it's not going to be as soluble, because it's quite happy being a crystal compared with the metastable form here. And this was a problem for UCB. It was a big problem for Lilly with ritonavir. They progressed form 1. They'd even patented form 1 and agreed with the FDA that was the form they were going to sell. And then in Southeast Asia, in hot countries, they started seeing form 2. And not only was this less bioavailable, they had another problem in that contact between form 2 and form 1 turned form 1 into form 2, and it contaminated their factories, and they were unable to make form 1, which was the one they'd agreed to sell. So they had to spend millions in actually trying to find a way to make the original metastable one and then keep it as the metastable form by refrigerating their supply line and so on. These are the kinds of awful, costly mistakes you don't want to make. So a little bit of computational chemistry can help you in this kind of safety assessment. And then the other thing is expensive quantum mechanics I mentioned. You're only interested in the one molecule. You're interested in purpose-designed catalysts to make that. In some cases, the route that the discovery chemists used to make the material was probably 12, 13 steps, knowing them. And we want as few steps as possible for development. And oftentimes you do this with purpose-built catalysts, which is designed specifically for that one molecule. And you do a lot of crystallization for purification and things like that. So I've actually worked with development chemists to design catalysts. My most successful one was we designed a specific catalyst which removed 4 steps from the synthesis and saved £1 million in making a kilo for clinical trials. There are other interesting things you can do. We found another problem where we had to do some QM calculations because the solid form, the crystal, was susceptible to light and it converted to an inactive compound. There was an in the solid state reaction going on. So we had to design new forms of that to actually mitigate that. Otherwise, you'd have to make it in a dark factory, as they call it, a factory under something like yellow light, where it didn't convert. And synthetic biochemistry, that's an area where you design new enzymes. I designed an enzyme which is used in the factories for making some of the penicillins, for making amoxicillin, where we designed a new penicillin G acylase, which is part of the procedure for making 6-APA, the intermediate, which is 6-amino penicillinic acid. And there's more details to that in this particle informatics paper. So some things I haven't talked about, systems-based approaches. They've been trendy now and again over the years, but I think the computer's now fast enough and there's enough data so that you can make a stab at some of these things. Dose prediction is coming along quite well. If you have a few molecules in the same chemical series that you've tested, you can generally understand enough about the processes going on in the body, the fate of the molecule, whether it's eliminated, unchanged, or whether it's metabolized and that kind of thing, to actually build up a model for dose prediction that works quite well. People are building models of organs and cells and things like that. Biovia, for instance, have got a mechanical model of the heart that's purely computational. It is just mechanical at the moment, as far as I'm aware. It's not to the level of biochemistry, so you can't see chemistry in it, but you can see some of the effects of changes to the valves in the heart and how that affects the beating of the heart and things like that. So it's starting to get there. And then there's other non-traditional areas, PROTACs. This is an area where instead of inhibiting your target, you actually get the body to eliminate it by ubiquitination. Now there's computational chemistry opportunities there in designing the linkers and designing the warheads and things like that in the first place. RNA comes up every so often, quite complex area, much more interesting than DNA, lots of different structures. And again, the structural language is, I think, being better interpreted these days. I mentioned synthetic biochemistry. And the other thing you'll come across in computational chemistry, because as I said, it's all about ideas, is every so often, and when I say every so often, I mean every couple of years, someone will come along to say, this thing will revolutionize drug discovery and we won't need any more chemists, we won't need any more biologists, or indeed we won't need any more computational chemists, depending on what the thing is. I suppose I rode into computational chemistry on the back of this, molecular graphics. In those days, computer graphics was a new thing. And people thought that just seeing an image of of a molecule on a computer screen would be enough for us to suddenly realize what compound we should be making. That didn't quite work out. FEP, which is now a well-established technique. I did my first FEP calculations in the late 80s, and I had a PhD student at Oxford doing calculations in the late 80s, early 90s. They didn't work. The computers were too slow at the time, but we could see where it was going. And then Combichem, I mentioned something about Combichem before, didn't I? The huge library. That was in the mid-90s when we thought that if we don't need to design anything because we just make everything and test everything. Unfortunately, there's about 10 to the 25, 10 to the 60 different possible molecules, depending on who you believe. But there's many, many more than you can have in a combinatorial chemistry library. So that didn't quite work. Going through to today, AI/ML is very trendy at the moment. And we're starting to learn what it's good at. As I said, recognizing data and filling in, and what it's not so good at. I'm not so sure big data is ever going to amount to anything. I'm not a great fan of that. Right, the future of computational chemistry. Well, I've ducked this one. Unlike Kevin, who actually predicted the future, I'm not going to. I'm going to tell you about recent trends that I've observed. This is an interesting one. The ratio of synthetic chemists to computational chemists keeps falling. I remember writing a white paper for senior management back in about 95, 96, suggesting that we change the ratio of chemists to computational chemists from, it was about between 40 and 60 to 1 at the time, to we wanted to go down to about 12 to 15 to 1. We thought that was a better ratio and allowed us to have more bang per buck. And that was by recruiting more computational chemists. Now, at GSK, I think the ratio is about 4 to 1 now. And that's not because we've hired a load of computational chemists, it's because synthetic chemists have disappeared. Most of them, there are a lot of chemists, but they're not working for GSK. They're in outsourced groups in China and India and Peakdale and wherever. So the ratio has changed markedly. So it's an interesting one. If you want a career, do you become a synthetic chemist or do you become a computational chemist? I'll let you decide. This is a bit of a truism. The nearer you are to the IP, the less likely you are to be outsourced. That's quite good for computational chemists because we're all about ideas. Though I would say being outsourced is not a scary thing these days. In fact, most of the jobs are in outsourced organizations rather than big pharma, I think, and a lot of the more interesting work is there. And that's also because of COVID. COVID's changed work practices markedly. There was a big suspicion about working at home before that, but of course people have been working at home for 2 years. And it has resulted in some interesting things, like, for instance, the Philadelphia group of GSK was always pretty stable. It was a nice place to live, much cheaper than living in Boston or California, where the larger money jobs were. But now, of course, with COVID, they were working in their back bedroom or their office at home, but they could equally be working for someone in Boston or for Google in California as for GSK. So a lot of them are left. They haven't left the area, they're still in Philadelphia, but they're working for Californian companies. So that's an interest. That's a bit like this. This is this small mobile and hopefully intelligent units thing that Robert Fripp said in 1974. And of course, there's a world shortage of lots of things, and one of them is computational chemists. So finally, my recommendations, I know I've run over time a little bit, because all you're good at is ideas and influencing, then you should study design. There is some, for instance, some good books by a guy called Stephen Few about getting your ideas across. I'd recommend them. I wish I'd had a better understanding of statistics early on. It's not difficult, it's actually quite simple, a lot of it, but it would help with discussions with assay scientists. And finally, if you're a generalist like me, aim for versatility. Be interested in new things, see how they might apply to your project. Be prepared to work in different areas. As I said, I've worked in synthetic biochemistry, I've worked in development, I've worked in early and in late stage, so which I think is fun. If you're a specialist, I think you have to be a world expert. You've only got the one hammer to hit every problem with it, so it might as well be the best you can be. So, and I think that's it. Oh yes, I've just got a summary, sorry. Oh, by the way, this picture I had before, that's me. This is when molecular graphics, I was saying, was hype, and this is the Beecham annual report to shareholders from 1987. We had a picture in it. That's me, and that's Paul Finn, who was the other computational chemist in Surrey at the time. So yeah, the only thing that big pharma has, apart from a few resources, is data. If you're not using the data, you shouldn't be in big pharma, I don't think. A computational chemist can work at all stages of the process, it's probably best to choose whether you want to generalize or specialize fairly early, I think. And it's all about influence. I hope I've shown you some ways that computational chemistry can influence drug discovery and development. And thank you for listening. That's it.
Thanks very much, Colin. That was a really interesting talk. I don't know whether you want to switch off your screen or come up on her.
Oh, sorry. I thought I had.
Which is your preference if you want to put your camera on or anything like that. Can I just ask if there's any questions here in the audience for Colin? None yet. I was actually just wondering, Colin, you gave us some really interesting examples there, because I mean, what I work in is kind of drug discovery from a biological perspective. And, you know, my aim is always to find the best molecule, but I suppose I don't think past that. And you gave some really interesting examples of kind of, you know, where they had gone through all of the stages of it and kind of, you know, during manufacturing, then there's kind of issues and the molecule changes. Like, how frequently do issues like that happen? Is it quite common or is it quite rare?
Oh, yes, very common. I think a lot of companies like GSK pride themselves on having very, very good formulation groups that can get around all these issues. So, and that's led to a lot of complacency amongst the discovery workforce, that they can just send anything to development and it will end up being a drug. And I think it would be, and unfortunately GSK has one of the, for that very reason, has one of the slowest pipelines in the industry. And I think that's because they have to keep reformulating and addressing ideas, coming up with new ways of milling hard material or material that squishes into the mill and glues around the outside, and or doesn't pour well, or it's got static, or the sticking and picking when you print out the pills, and you can get problems with sticking to the press and things like that. There's many issues in properties that we just don't deal with or even think about in discovery. We just let them worry about them later. And it could be that you just chose a different molecule that has different properties, and then it will sail through development a lot quicker and easier. Yeah, so a better kind of rational design at the start. Or being more selective, maybe kind of what you bring forward. No, that's very interesting. And then I suppose, I mean, you've spent many years working for, you know, obviously for pharma as well, but coming from academia. Would you recommend it to our biologists and computational chemists here in the audience, then working for the big pharma and things like that? Like, what would your thoughts be? Yes, I realize there aren't that many opportunities because there aren't that many big pharma companies left these days. Though that's the same when I started. When I started, there were no big pharmas, they were only medium-sized. And they all merged together to form the big ones. Because I started to work for Globachem, which was a medium-sized company at the time. And I think it's only useful if you actually are interested in data and going back and looking at the data and using the data that these companies have amassed. I'm not saying it's easy. You know, a lot of the data is rubbish, and a lot of its, particularly development data, is hidden away in PDFs. I think that's probably one of the worst things to happen to science, is the PDF, because they're very difficult to extract data from. True. But I think medium-sized companies like I started with are really, really good places to work, because they're big enough so you've got some kind of career trajectory. You know, you can become the head of a group, or you can become the head of MedChem or something like that. But also they're a bit more flexible. One thing I've noticed just working with Cresset over the last few months, I only started in November, is decisions are made like that. Whereas in GSK, decisions take 6 to 9 months and then come back asking for more data. So you do get a lot of the large companies that are quite ossified, and it's very difficult to change the direction of the supertanker. So I think it depends on your temperament really as well. You can get very frustrated in these large companies if you come up with some new ideas. Or it can take off and you're suddenly in charge of a department of 80 people. That's great. So I'm just going to check and see if there are any more questions here. Okay, well, look, other than that, thank you very much for a really interesting talk. And I hope we get to meet you one day in person as well. Thank you, Colin. Okay, thank you.
And I think we're having a break now until 4, is that correct? Yeah, okay, so we're just at 3:28 now, so just half an hour. And to go take a look at the posters. Great, perfect, thank you very much. Hey, will I let Colin go then? No, that was great. I would ask him more questions.
I think we should choose group.
He is. Just thanks very much, Colin, for joining us. If you're still there, we really enjoyed that.
Thank you.
Yeah, okay, yeah. Thank you.
Yes, thanks very much.
You're fine, maybe we turned off the microphone.
No, that's fine.
Perfect. Correct. So I can. Hello, Edith. So the screen. Okay, she's panelist now. Yeah. Yeah, I can
And then you can then just, what I did is just turned off the microphones, just, no, just after I finished talking, so that,
yeah,
you know,
after
so,
I finish.
yes,
Yes, perfect. So welcome back to the last session of today, last but not least. And I am delighted to present Professor Edith Chan, who is Associate Professor at University College London. Edith is an Associate Professor at the Wolfson Institute of Biochemical Research, and she has worked in pharma and biotech, and her research interest is all spectrum of computational drug design. So Edith, the stage is yours. You can share your screen. All panelists is correct.
Okay, can you all see my slides?
Not yet,
Not yet.
I guess you can see it now.
Yeah, perfect, thanks.
Yeah, thank you for inviting me to this workshop. I hope you guys learn a lot this morning. So before I started my presentation, just want to tell you something about myself. I got my PhD in theoretical chemistry in Cornell a long time ago. And I work in pharma, Itapharmaco, Sanofi, and also biotech before I joined UCL about 10 years ago. In UCL, we totally encourage internal and external collaborations, as this is very important. I guess if you work in academic, you see how important it is to have this kind of a collaboration with different people. And it also will enhance the grant writing procedures. In UCL, we have organizations which deal with translational projects. And it does really bring together multidisciplinary approaches for a lot of departments. And I find it very useful to have the opportunity to collaborate with other people. So computational chemistry and molecular modeling support many projects within UCL and also external collaborators. And my research interests cover really a wide spectrum of drug discovery, related molecular modeling, computational chemistry, chemomathematics, and so on. Cresset want me to give some case study from molecular modeling or computational chemistry support in different projects. So today I'm going to give you two examples. One is what we call structure-based drug design, and the other one is ligand-based drug design. Now, so this slide looks really, really complicated, so I'm not going to talk about all of this. I just want to show you that molecular design or molecular modeling is a really mature and still flourishing fields in drug discovery disciplines. There are so many established algorithms and approaches, strategies. So when we talk about structure-based drug design, usually there are some protein structures, whether they are from X-ray or NMR, and they could come with or without ligands or inhibitors. So in the case of X-ray, it could be co-crystallized in the binding site. And then in a top level sense, we will use these structures, design new compounds for biological testings. For ligand-based drug design, is not so fortunate. Usually, it does not come with any X-ray structures of the target protein. But very often, it will come with maybe a set of ligands or a ligand with or without biological activities. And sometimes we might have some ligand informations, but we do not have protein target informations. But even for the most difficult cases, there are always some approaches, computational approaches that one can use. So the first example, the two examples that I'm going to give you, both are published. So if you are interested in other aspects of the project or the study, you can please go ahead and look at the published paper. So the first one is a structure-based drug design case study. And it's a collaboration with me and a couple of chemists in the Department of Chemistry, and also my colleague at the Structural Biology Laboratory. And the protein target is histone deacetylase 8. So HDAC8, it is a protein that has been studied quite often already. It catalyzes the acetylation of lysine residues, resulting in chromatin compaction and transcriptional repression. And the therapeutics area could be cancer, heart disease, and neurological disorders. Some HDAC inhibitors are already used in cancer therapy. And the upregulations of HDAC8 strongly correlate with the progression of juvenile neuroblastoma. So what do we know? So let's look at the inhibitors. So in fact, HDAC is a zinc-dependent enzyme. So that means that in the active site enzyme, in the active site, it has the same metals and a whole bunch of histidines and aspartic acids. So for the past so many years, a lot of the inhibitors have been made, and basically they are all hydroxamate acid moiety, which I have labeled in this purple circle here. So if you're a chemist, you will know that this kind of motif is really good to stabilize metal ions, as well as charge and polar group. In this case, the aspartic acids and the histidines residues. So they are quite good, and so everybody will make something with the hydroxamate acid and then extend whatever group is necessary for the bonding in the bonding site. However, hydroxamate acid confer limitation of efficacies, and also it is toxic. Novartis has reported a different structures for bonding to HDAC, which is this box here. And you can see it doesn't have that horrible acid motif anymore. It's that it has this a primary amine group. And what is even better is this compound comes with a crystal structures with HDAC, and it's deposited in the protein data bank, PDB. The primary amine here is used to stabilize the zinc atom in a bonding site, and the rest of the compound have hydrophobic interactions in the active site. So the graph I show you here is a 2D schematic of the interactions between the inhibitors and the protein itself. So the dotted line you see here is hydrogen bond, and the eyelashes here are hydrophobic interactions. And like I say, a lot of our algorithms for modeling, you can actually pick them up in public domain. Okay, so what are we supposed to do? So our goal is actually very clear. It's to find a better inhibitors for HDAC8 using the Novartis scaffold, and to achieve better IC50. Now, the methodology we use is we are going to survey is a family approach. We're going to study all the PDBs of different HDACs. Why do we want to do a family approach? Because HDAC has a lot of subtype, and we want selectivity. So by looking at doing the sequence and structures alignments of all the HDACs, we could be able to analyze the bonding sites, find out key residues that are common or different in the bonding for different HDACs. And then we can also understand the ligand protein site interactions. And then once we have gathered those kind of information using modeling and computational chemistry techniques, we can think about design of the new compounds. And this process is sort of like a discussion process. So with this information, we have scientific discussions with the chemists, with the structural biologists, and then we can come up with some new ideas for further computational evaluations, which we call 3D docking. So in simple terms, basically, we look at different conformations of those virtual ideas and put them into the binding site for energetic considerations. So this is what we call 3D docking, and they come in many, many different forms. And then we will evaluate the virtual compounds or ideas and prioritize synthetic effort. And then subsequently, the chemists will select a group of the ideas or compound, synthesize them, and then put them into biological testing. So just to give you a little bit of what we did to prepare this docking. So the PDB I talked about before that have the Novartis compound and the H8 is called 3FSH, and it's also a good starting point. However, so this is the C alpha chase in helical in schematic form for the protein, and the gray surface here is the binding site. And this is where the Novartis ligand bind into the binding site. However, because we are using family approach, and immediately we can see that a loop is missing in this 3FSH site. And this loop actually, if you compare the structures and sequence, it is quite crucial in bonding. So before we even can do docking, one of the molecular modeling technique we use is fix the loop. We fix the loop, we prepare the binding site, and then we can think about docking. And as I said before, family approach is also very good to find out the key residues for selectivity among different subtypes. So the residues that are really important in that missing loop is the APS, aspartic acid. And it's the side chain of the aspartic acid is pointing directly into the binding site. And this is ideal for a hydrogen bond design. So just a rough thumb, I mean, without high level of calculations, a good hydrogen bond can offer 2 to 5-fold better activity. And this loop, so the reason I think that also that 3FSH loop is missing because the ligand compound does not offer a hydrogen bond to the apps to stabilize the loop. So I think the chemists make about 30 compounds of this series, and here I show you 4 compounds. So in this graph here, I hope you can see my cursor. Is the original Novartis 2 compounds, and the dotted line here just show is not hydrogen bond. It's the pi-pi interactions between the 2 aromatic rings. So we make 14A and 14B. One is with the amine of this bicyclic ring, and one is a acylated nitrogen. And both have very similar activity, but nevertheless slightly better than the Novartis 2 compounds. So these are not X-ray crystal structure. These are the docking result. So it's a predicted result. So 14A and 14B both are predicted to pick up this hydrogen bond with the Fs 101. So of course, we also make other compounds just to try out different hypotheses. One of the compounds we make is instead of a bicyclic ring here, we make a 6-6 bicyclic ring. So the docking result also show that, you can see that bioactivity is much worse. And it seems that from the docking result, it showed that the pi-pi interaction is sort of like worsened because the volume of this ring, the bicyclic ring, has pulled away from the phi152. So for conclusions, we have made a better compound, and in fact, we have made a series of better compounds than the Novartis 2. 14B is the one that we think is the best. And we also have tested it in different HDAPs assay, and it's highly selective in HDAP 8. because in like 1, 2, and 6, they have really, really much worse activity. So the take-home caveat is interacting with the apps 101 is really important. And also in mutation study, it's, if you mutate the apps 101, it will lead to loss of inhibitions of HDAC. Okay, so the second example I want to give is a ligand-based drug design approach. This is a collaboration with the Neural Signaling Group and also the Medicinal Chemistry Group in the Weber Institute of Biomedical Research. And it's about antioxidant. So again, I give you the link for the full paper. If you are interested in this, please go ahead. What is it? Lipid peroxidations or oxidative stress is implicated in neurodegenerative disorder, for example, motor neuron disease, multiple sclerosis. Severe lipid peroxidation triggers a form of cell death. Our brain is particularly susceptible to oxidative stress because it's full of unsaturated lipid content. Lipid peroxidation is initiated by radical species such as the hydroxy radical OH. This damaging preoxidation could alter membrane property and impair mitochondrial functions to cause cell stress. So the group found that in rat brain, it consumes nitric oxide or NO in a lipid peroxidation dependent manner. So inhibiting the NO consumption could prevent lipid peroxidation. So as of now, possible treatment for lipid peroxidation could be metal chelators, ascorbate depletion, or antioxidants, which there are some known cases in the market like Charlox or Lacerate. And recently, there's a new drug, Redicover, is approved in USA and also in Japan for recovery following a stroke and to treat ALS, is a motor neuron disease. Now, why is it so special? It's because the other therapy that I was talking about, they are mainly, they are all basically natural products. And this is a first-in-class chemical structures. It's an antioxidant, but however, the mode of action is not known, so we just know it works. And there's another unfortunate thing is this, even though you look at this molecule, it looks so small, it is not orally administered, it is via IV. However, it still generates a lot of new interest in developing antioxidant. So our aim is to discover potential antioxidant molecules only by virtual screening. We do not want any chemistry efforts because we actually we don't have the budget for it. And also the biological experiment were really labor and material intensive because we have to harvest the brain cells in rats. And then of course, molecules should be physical available and purchasable because as I say, no chemistry effort. And to do this, we start with some known antioxidant structures. So we want to compose a set of compounds for the initial screening. For that, for the first round, we only look at the in-house chemical database because the medicinal chemistry group and the neural signaling group has been collaborating for a long time. So actually they have a lot of collections of molecules that target different proteins in the brain. So we use a couple known antioxidant structures and we perform some searches, 2D similarity search and 2D substructure searches into this in-house chemical database. So I don't know if this morning you guys come into this kind of concept. So for example, like we have a structure here, right? these 2D structures, I mean, in a it has different type of bond type or functional group, and all of this can translate into different kind of fingerprints. So basically, we can like translate different molecules into fingerprints. And to search, to compare fingerprints, whether they are similar or not, of course, this technology has existed for a long time, and we can apply this to chemical structures. And usually the matrix that we use is called Tanimoto. And there is a published paper a long time ago that if the Tanimoto index between 0 to 1, 0 is totally not similar, and 1 is completely the same. If the Tanimoto is bigger or equal to 0.85, it can imply that the molecule could have similar bioactivity. So that's what we call 2D similarity search. And 2D substructure search, basically, if a set of molecules have the same scaffold, like this one here, this tricyclic ring, then you can use it to find other compounds that have a similar scaffold too. So with this exercise, we found about 30 compounds for the initial biological cell-based testing in a nitric oxide inhibition consumption assay. And only 7 compounds have very, very good activity. And 3 of them have the phenolphthalein scaffold, which is this tricyclic scaffold here. So for our second round, so we only use 2D substructure search of this phenolphthalein scaffold with this CR linker here. And then we use it to search in-house and also commercial databases. And we have assembled 61 final compounds for testing in the same assay. 15 compounds have less than 1 micromolar activity. So the hit rate actually is quite good, it's 25%. So 1 in 4 compounds that we select are active. And subsequently, we select 1 best compound, which is compound 26 for in-depth profiling, biological and physiological profiling. Now, after we've done all the testing, and so you can call that compound that we find is a hit compound or hit series. And the next stage in drug discovery process is we want to bring this hit compound into a lead compound, and we call that lead optimization. And for a computational approach, we would like to know how to relate the structures and activity. And for this, we call this QSAR, quantitative structure activity relationship. And in this case, we have a good set of compounds and activities. So we want to establish a predictive model. So because in the future, when we want to make a new compound, we want to test the idea in the computational model before making it, right? So we use a technique called partial least squares or multivariate partial least square method to produce model using only 26 structures in the IC50. And you might ask me, well, you tested 61 compound, why don't you just throw them all in? But you know, we have a famous saying in computational chemistry, garbage in, garbage out. So we don't want that. So we want to establish a subset of compound that can achieve a good balance of diverse outgroup, as well as like half active compound and half inactive compound. Because if you just throw in all the active compound, it wouldn't give you any good model. Anyway, this is the result of the study, and this is plotted for log IC50 observed and also predictors. So we obtain more or less a linear curve, which is a good sign. Also, the R square is 0.9, which is indicating that it's a good model because when it's 1, it's perfect. But however, so we do have a model. So in the future, when we make compound, we're just going to throw this into this QSAR model and see whether we should make it or not. But for us, it's still not satisfying because, you know, for us, we want to know why is it active? Why is it not active? Because most of the compounds are not active. So to do this, we employ the Cresset field analysis, which I think you have learned this morning, because it could tell you what's going on. So here, I only show you the most active compound, 26, and the inactive compound and see what's going on. So another way that for maybe biologists to think about how to, I mean, for me at least, to how to think about this field thing is if it's too mathematical or abstract for you, is how the protein, the target protein, see it. So the best compound, if you look at it, it's really striking. The result is really striking and nice. You can see that near the tricyclic scaffold, phenolphthalein scaffold, the field is totally positive. But when you change this R group into something very different, and the field is changed completely to negative. So I think it can really explain nicely what's going on. I mean, well, so so for us, when we are making compound in the future, we will pass those ideas into the QSR model as well as the Cresset field analysis before determining what to make. So for conclusion, the phenolphthalein-based drugs have been reported to have antioxidant potential. So it has a higher odds that we know that it will work. Compound 26, this compound here, is an extremely potent compound. It's 100-fold better than radicarva. We have carried out many additional biological experiments on this compound. It's also highly potent in hippocampal slice, highly selective and no observable activity against other NO synthases in rat. The low molecular weight of 26 could improve BBB permeability. So, you know, if the drug is oral, is much better than IV, which you might have to go to the hospital to get it done. And then the caveat is the prediction model could help future lead optimizations. So I hope you like my 2 case studies, and if you want to ask me anything now, I'm happy to answer. Thank you.
Thank you very much, Edith, for the very interesting talk. Are there questions from the audience? Yes.
Just wondering how did you perform a difference between the HTAC1 and HTAC8, meaning that the same aspartate residue is in that position and so for the region. How did you rationalize the difference in the selectivity?
Could you hear the question?
No, I think you need to repeat it to me.
So it has something to do with the selectivity between HTAC1 and HTAC8. Okay, now I got it. Because the question is, it seems to be that they have the aspartate residue in this in a similar region. So how could you distinguish between?
I'm sorry, I can't remember because I did this a long time ago. Yeah, so maybe there's another region that the residue could be different. So I'm sorry, I couldn't remember the sequence alignment of what residues. But it's always good in any case if you have more than one subtype of the protein, line them up and see where you can make your special design.
Thanks. There was another question? No? Then I have a very naive question. And at the beginning, you were mentioning, you were presenting a structure with a PDB number and saying this is a good point to start and for docking. And I'm just wondering, as I'm often looking at PDB structures, so what, in your opinion, is a good PDB structure for a docking? So at first I would just look at resolution, of course, but are there also other things that you think is important to take into consideration before starting a docking experiment?
Yeah, resolution is very important. I think for drug design, less than 2 angstrom is good. But I think from my experience, if your inhibitors or ligand resemble the co-crystallite ligand in the PDB, you should also use that too. Because sometimes that, you think some of the side chain haven't moved, but I mean, microscopically. I mean, we cannot see that in our human eyes. And there might be some special interactions with the ligand that you're interested in to be in the active site. So that is very important. So, and very often when we are doing docking, we might not just use one structures. We might use a couple structures to have a look, to have a look at the evaluations of energy, what result it's giving you. So it is more like really like experimental work. It's not just I pick this structure, this ligand, and just that's it. I mean, it's not like that. Sorry, my answer is too flexible, isn't it?
Yeah. Okay, thanks for this answer. Other questions from the audience? Otherwise, I think we have a question in the chat. Is the small size of radicava very unusual for a drug in clinic?
No, it is quite usual. Why is it unusual? Because so just rule of thumb again. I don't know if you guys heard of rule of 5. So rule of 5 measure different property of drug molecule. So mainly molecular weight and C log P. So usually the smaller if the molecule is smaller than 500 molecular weight, usually it will has a tendency, it has potential to be a potential drug. So I think the unusual thing is it's such a small molecule. Why is it not an oral drug? Does that answer your question?
I hope so.
So it is not unusual.
Okay.
Yeah.
Thank you.
Okay then.
If there are no other questions, then thanks again to
Bye, guys.
Bye. And then let's present the next and last speakers of today. That is Victoria Jackson from Operating Officer Globachem. Let's see if I can make her panelist. Okay, perfect. So I don't have to do anything. So welcome, Victoria.
There.
There you are. Nice to meet you. So Victoria Jackson graduated from Bath University with a first-class master's in chemistry with industrial experience and took up a position with Celltech Chiroscience later to be UCB Pharma in 2002. Victoria has over 12 years experience as a medicinal chemist and principal investigator working in kinases and protein-protein interactions in the areas of oncology and immunology. She was also project manager for the global development of a phase 2 clinical development compound for multiple sclerosis at UCB Pharma. Victoria then took a role at Redac Crop Protection, located in Alderley Park, UK, as the first employee on site and chemistry team leader in 2014, establishing and leading a team in early stage research and discovery of novel agrochemicals. Victoria was appointed as operating officer for Globachem Discovery in 2019, when Redac was purchased in an asset sale, and continues to lead the UK research and development group of the Belgium agrochemical group Globachem. Victoria is a chartered chemist, ACS member, and committee member for the Royal Society of Chemistry Agricultural Sector and committee member of the SCI Fine Chemicals Group. She is author of over 30 patents and several publications. And Victoria, the stage is yours.
Thank you very much for that kind introduction. I hope everybody can hear me okay over in Dublin. Does it sound okay?
Yes.
Good. All right then. So I gather I'm the final talk of the day. So I hope I can keep you all going on the story of agrochemicals and agrochemical discovery in collaboration with Cresset. So today I'm going to talk to you about scaffold hopping and bioisosteric approaches and alternatives to macrocyclic picolinamides. We work at Globachem on a number of projects. We work in agrochemical plant protection products for fungicidal diseases. We work on herbicides, and we work on insecticides as well, and looking at plant growth control. And this particular project I'm going to talk to you about is fungal diseases, and in particular disease control in wheat. And why we're looking at that, it's incredibly important, especially within Europe and within the UK, to look at our cereal crops and how disease impacts our cereal crops, such as wheat. So Septoria tritici is one of the most important fungal pathogens, which causes damage to winter wheat here in the UK, and it can have real impacts for our farmers and how it can impact on the yields of the crops from anything from 30 to 50% as due to high pressure and disease, and depending on the seasons as well. Another type of fungicide is brown rust, especially in barley, so we can look at that, and other types of rust such as yellow rust. And they can also impact on crop yields, and losses can be from 15 to up to 50%. So it's really important that we look at having plant protection products which can control these diseases, which can help farmers to maintain really good yields of their crops. So that's something that's really important for us. When we're looking at fungicides, we also have to look at the impact of overuse of fungicides that we're seeing within certain countries or within globally, that can have impact on resistance within crops. So we're already seeing within certain countries overuse of certain classes of products which have specific modes of action. So there might be increasing resistance towards triazoles or strobilurins, for example. We can see that. So it's important that we look at sustainability of products, which can help focus and target on these types of resistance that we're seeing emerging. Where we look for starting points is we can look at natural products for agrochemicals in the same way that you can in pharmaceuticals. And natural products account for 18% of crop protection compounds. However, when you look at some natural products and when they're identified, they can be quite complex molecules. And with that, they might be difficult to access. So you might have to look at fermentation processes rather than looking at chemistry to chemically synthesize these molecules, because they can be quite difficult. Also, when we look at some natural products, whilst they are good starting points for agrochemical projects, they're not always developable or registerable, because we can have issues with photostability, for example, which was seen from the strobilurin starting points, natural product starting points. We can also have problems with soil degradation. It might not be optimal for us, and they might not necessarily have great bioavailability in the field. They might work well in a laboratory setting or in the greenhouse. However, when you go out to the field, you've got environmental factors to consider. So they might cause us issues in terms of the developability and registrability of natural products. And they can also be quite expensive to develop, particularly if they've got a lot of chiral centers in them, or that, you might have to do a lot of regulatory work to develop these natural products. So we can look at natural products as starting points for further synthetic modification, or we can look at them for structural simplification to lead to further agrochemical products that are more registrable. And bioisosterics can offer a potential to address several of these issues that we've discussed. And there's a really interesting paper by Sparks in the Journal of Agricultural Food Chemistry that was published last year. So I'd encourage anybody to have a little read of that. It's a really good paper. So what I'm going to talk to you today is about the fungicide mitochondria, and within that, the cytochrome BC1 complex. Within the complex mitochondria, there exists parts of it, and we'll be looking at particularly complex 3 in the BC1 complex. And this is really an interesting mode of action in terms of how this is role for septoria and for rust diseases and fungicides. And UK2A was identified from soil-borne streptomyces, and it was originally identified by a Japanese group. And we've got the structure here of UK2A, where you can see that we have a core macrocyclic ring and a picolinamide amide here. So yeah, it was originally identified by the university in Japan. And from that as well, already from UK2A, there's a similarity in terms of the core and in terms of particular bioisosterics with picolinamide and antimycin. And both these compounds act within the QI, so the quinone inside site within the cytochrome BC1 complex of the mitochondria. And this is a site that's also identified within the septoria mitochondria for fungicidal mitochondria. So these are really interesting natural product starting points for a project. However, you can see they're quite complex as well to chemically synthesize. So the UK2A was taken as a starting point by Dow, who is now through mergers and with DuPont, the company is Corteva, and they developed a product called fempicoxamide. So taking a natural product starting point, UK2A, they did a simple structural modification, and I've highlighted it here, where they look to protect this hydroxy group within the picolinamide to a pro-pesticide. And they did this, as I said, to promote leaf surface stability. So one of the issues I've talked about just in the previous slides, where when you take a natural product, it might not always be developable due to stability and bioavailability in the field. And this is what Corteva did to really maximize the amount of compound which is bioavailable, make sure that it sticks on the leaf and can then be delivered in the plant through to the active site. So this was a new class of fungicides within the Fungicide Resistance Action Committee Board of Action Group as C4 number 21. And they inhibit the mitochondrial respiration, they block electron transfer in the respiratory train, and then, as I said, it binds to complex 3 at the quinone inside site within the inner mitochondrial membrane. And this is a novel mode of action which is different to other fungicides that might act within the quinone site. Strobilurins act within the quinone outside site. So it's within the mitochondria, however, it is within a different binding site within the mitochondria that these are acting in. So it's interesting and novel, and fempicoxamide was registered and approved in the UK just last year, and it's being approved subsequently across Europe as well. So Inatrec is the first generation molecule. However, you can see that it has a 9-membered macrocyclic core ring. Again, you're still keeping the various stereocenters here. So there's a degree of complexity with it. And the way that they generate Inatrec is through fermentation of UK2A, and then obviously that synthetic modification to make the pro-pesticide for field stability. So it's quite expensive, and when we think about the end product, we have to think about the farmers, we have to think about the costs, and cost of goods is a really important factor in when we develop our molecules and agrochemicals. They have to be cost effective for the farmers, because obviously they're going to be applied in the field and we need to use quite high volumes as well. So with Inatrek being the first generation product, but still quite expensive, Corteva worked on really looking at the molecule, identifying chemically what parts of the molecule were necessary, and doing some chemistry to look at modifications to produce the molecule Adavelt. And this really is a linear compound. They've removed the need for the macrocyclic ring, and it's available chemically through natural amino acids. So it's a little bit easier to synthesize and therefore more cost effective. Again, we've kept the picolinamides, which is the key pharmacophore for binding. However, we still have to protect up that hydroxyl group for leaf stability and permeability. So it's a simplification of the structure. However, we still contain some stereocenters in there as well. And this is the second generation commercial product, which is coming from Corteva, which isn't on the market yet, but will be coming in the next couple of years. So moving forward, what we were looking for in-house within Globachem is really how can we identify novelty in our own position within the project. And really going back to Inatrek, the original molecule, we wanted to know, well, what is the bioactive conformation of this macrocyclic ring, and how can we mimic it in the most effective and efficient way, and really generate some ideas. So working with Cresset, we looked in the crystal structure database to see what molecules are available. We performed conformational analysis with Cresset, and we also did some molecular dynamics with Cresset Flare. So there's really a three-pronged approach in which we could really look at addressing determining what the minimum bioactive conformation was, and then we can use that to generate further ideas forward. So there were two examples with that same central macrocyclic ring system within the crystals database, and they both shared the same cores, and they both shared the same macrocyclic conformation. So that was nice to see. With Cresset, we managed to look at conformational analysis by calculating the global energy minima of that central ring, and look at that in comparison to the crystallographic information. And there was a very low energy conformation that was identified, and they seemed to complement each other quite nicely. So that was a good exercise to look at. And from that as well, we were also looking, as I said, with the molecular dynamics, using Flare to really extract all the possible conformations, minimize them and cluster them, and look at what the lowest energy conformation was through these three different approaches. And all three methods converged on the same macrocyclic ring conformation. And at that point, we were able to see they've got consistent points where we can look at growth vectors to put substituents on, to look at various points of building in the key pharmacophore, or perhaps looking at substituents to modify chemical properties. Apologies. With this conformation as well, we're also able to build a homology model. So looking at taking information, we can then look at taking the protein and building up the protein complex. There isn't an actual crystal structure with a Septoria mitochondria BC1 complex, so we're able to build a homology model with Cresset Flare, and then look at inputting in the Inatrek molecule or the antimycin molecule to then look at the complementarity within the binding site, to look at how the conformation of the molecule is fitting within that. And through that homology model, we can look at it really quite nicely to look at how Inatrek, the first generation Corteva molecule, how that sits within the key quinone inside binding site, and then look at Adavelt, the second generation, and we can overlay them quite nicely and look at the differences, perhaps of the growth vectors or the conformation of the nine-membered macrocyclic ring versus the long linear molecule Adovelt. So with this information, with the homology model we had and with the minimum energy conformation, we were then able to work with Cresset and look at, well, how can we replicate that nine-membered macrocyclic ring with something that's more synthetically accessible and which could give us a novel starting point, novel chemistry. And so we ran a Spark bioisosteric replacement, and this is just some of the examples that we've got, but we came up with a lot of examples through Spark. So we've used quite a lot of different software applications with Cresset to really help generate ideas for us to give us the best possible chemical starting points for us to identify novelty and synthetic tractability forward. So we looked at the Spark results and the output from that computationally, and we prioritized the ideas. So we looked at prioritizing them according to the log D in relation to Inotrec, the starting point, which had a log D of about 4. We looked at synthetic tractability. So for us, when you make an agrochemical, you kind of want it 4 to 5 steps, because obviously the more steps you have and the more synthetically difficult it is, the more costly it's going to be as a product. So you really have to look about synthetic tractability and accessibility and how that impacts on cost of goods. We looked at the scalability of the chemistry and can it allow for building blocks which can be easily diversified. And we looked at the potential costs of manufacture as well. And also with these ideas, we also looked at the intellectual property. Was there existing patents in that chemical space? And do we have potential freedom to operate? So these are all factors that we took in when we had the Spark output that helped us prioritize some of those ideas. And really what came out of the Spark was how we could mimic that 9-membered macrocyclic ring with a benzothiazole. And as you can see, there's really quite a nice overlay showing how the benzothiazole fits over that 9-membered ring, and looking at the electrostatics and the electrostatic complementarity as well. We can see that the charges and how they overlay show a good electrostatic fit. So for us, benzothiazoles as chemists, we can make them quite easily. It can allow different points for diversification or points of where we can do further chemistry to get the right groups in the right place. So benzothiazoles was a good starting point for us. And that led to initial hit discovery. So we made GD1179, just a simple benzothiazole, and we ended up with an EC50, so effective concentration of 9 ppm, which for us was a reasonable starting point. And then with some further work and looking at points of diversity, we made GD1356, which showed by putting the phenoxy group in the 6th position, we could improve affinity and binding affinity. And then putting in obviously our preferred methoxy hydroxy picolinamide, it led us to 1369, which had an effective concentration of 0.1 ppm, which for us was really a great sort of hit to lead confirmation. So with that, we looked forward to really looking at the growth vectors of the core and how they complement or are conserved from the benzothiazole and how they compare to the 9-membered macrocycle. And we obviously used the Cresset software to look at the electrostatic fields and the electrostatic complementarity within that as well. The picolinamide is like a key warhead. It's a key pharmacophore, and you can see how it's quite conserved within the 2 different structures. So that gave us confidence that obviously we've got a degree of flexibility around the core and the linker, but we are looking at it's quite a nice, simpler alternative to the 9-membered ring. And we also looked at docking our molecules, so docking the benzothiazole and seeing how that looked within the homology model compared to Inatrec itself. So there's a degree of space within that helices pocket in the active site. So we were able to look at that as well with Cresset flare. So when we're looking at bioisosteres, and looking at the molecule, we're able to take it into 3 pieces. So as I said, the picolinamide really is the pharmacophore. That's your warhead, that's your key binding, which we've conserved. We've done a lot of work in this area and it's very difficult to replace. So for the project, we looked at where we could get scope for opportunities in our own chemical space, and we identified that it could be around the core, the benzothiazole, and around the tail. So what I'm really going to do is show you some of the core modifications that we've done. So looking at the bioisosteric replacements, as I said, the benzothiazole was a nice lead for us at 0.1 ppm. And it's interesting to see that even as you go to benzimidazoles and methylated, not really good for us. We were finding it was moving to inactive. And the benzimidazole with the hydrogen bond donor in the core really wasn't as favoured. However, if you move to something like a benzoxazole, 1557, you can see that you can get back into areas of activity about 2 ppm, which are really quite more attractive. So we can show from scaffold topping bioisosteric replacements, we can generate some quite nice ideas and replacements for alternative design hypotheses. What we did as well is to look at, obviously, 1369. It does demonstrate control in planta. However, we did make the pro-pesticides, so we made an acetate and a further alkylated methoxyacetate, and we can see that we can get really quite nice control in planta. So not only does it work in a kind of against the pathogen in a sort of 96-well plate primary assay, we can show that we can go into a whole plant, and the molecules are being taken in by the plant, and they're getting into the fungus to control the respiration. So we can see that we have control against Septoria, wheatleaf blotch, and also against brim rust at between 250 grams per hectare to 125 grams per hectare in some of the molecules. So that's really nice to see that not only are our compounds providing activity against the pathogen, but they're also getting into the plant. So just a little bit of chemistry, because I'm a chemist. So just to show you how these molecules are made, we would take a substituted phenol, for example, and do an SNAR against a nitrofluorobenzene. And from that product, we can then do a reduction to make the aniline, and then build up the benzothiazole ring with the sodium thiocyanate and bromine. And from that, we can either take a protected picolinamide, because these things can be quite difficult to couple via classic amide bond formation, with sodium hexamethyl disilane and DMF. We can make the picolinamide and make the proside. Or we can protect this hydroxy by an acetamide and do a direct coupling as well to get our products. But as I say, it's quite simple chemistry, 4 to 5 steps to get a product, which is cost effective as well for potential scalability. So I know it's been a bit of a quick run through, but I hope I've shown to you today how Cresset has assisted us in really generating some novel ideas, and how we've used different software for different purposes to help us within the conformational analysis, and then the Spark and doing a ligand-based approach, bioisosteric replacement. It's enabled us to discover a novel generation of benzothiazoles, which are replacements, synthetic replacements for a natural product such as UK2A and semi-synthetic derivative Inatrec. The chemistry that we've demonstrated is scalable and cost effective, and we hope to bring this product to the market. So we've got further work ongoing in this project. I'd really like to thank the team at Globachem, all the chemists and people who have generated all the data. And I'd really like to thank the team at Cresset as well, especially Andy Smith, who's done a lot of work on this. So yeah, and I'd like to thank you all for listening. Any questions?
Thanks, Victoria, for the very interesting talk. Are there questions from the audience? No? So I would have a quick question. I'm not sure that is quick, but let's try. So at the beginning, when you were, perhaps I have misunderstood something, but when you were presenting the UK2A and the INATREC, so the UK2A has itself biological activity, or how was it? So from where did you start? So
yeah, so the UK2A is that has biological activity. So that was from was isolated from the basically the soil-borne, the Streptomyces bacteria. And so that's the active component that was accessed or identified. And it does have really, it's a really potent molecule against Septoria. The problem is that it's not bioavailable, as we say, it's not stable within the plant. So when you look to go to a field, that's where you had to do the semi-synthetic procide formation, because it's not stable on the leaf surface, the compound breaks down. So you need to make it a little bit more lipophilic and be able to translocate through the plant and get into the mitochondria. So that's why the INATREC is a semi-synthetic variation of UK2A. Yeah.
Okay, thanks. Because I was wondering something that I know about proteins that is coming now as a hot topic. Take a protein and make it to something completely different. So change the activity of that protein. So is it something that you could start, for example, from a scaffold that has not itself biological activity and make a modeling, or try, for example, a scaffold that presents low toxicity? I don't know, I'm just, yeah. And make it, so create another molecule based on a certain scaffold with a certain biological activity that is desired.
Yeah, I mean, you could do that. I mean, certain companies have their own preferred scaffolds from de novo design, and that's what a lot of companies do. I mean, chemists are, you know, are creatures of habit. They like their preferred scaffolds. They might know about certain things about certain projects. You know, it's quite interesting to listen to the previous talk. I mean, HDAC is a target within agrochemicals, especially when I'm talking about rust, fungicide rust diseases. However, you have to look at the mammalian target HDAC as well as the plant HDAC target, and you have to make sure that when you look at the targets that you select, that you have to be careful that they're developable and registrable, and you have to consider human safety if that target exists within humans, or whether, you know, it's a pharmacological target, and how different it is to you know, to a target, say, for an agrochemical as well. So I think you have to be very selective about the proteins that you look at, and really their selectivity and their developability as well.
Yeah. Okay, thank you. No other questions? Also, no questions from the chat. So thanks again to Victoria and to all the speakers of this afternoon session, and of the whole day, I would add. Good. Then the next task for you, for the audience, is to fill the survey that you have already filled this morning, but this afternoon you should do it again after you have attended the workshop. So please take the next couple of minutes to do this, and then there will be the announcement of the poster prizes. So now comes the big moment, the poster prizes announcement.
So it's a bit like the Golden Globes. I'll take my turn in the sun. So I'm just before I do that, I'd just like to say another thank you to Morgan, who has put a lot of effort into organising, and to Alison and Brendan and Marina for being part and parcel of the organisation. It's been really great sort of collaborating, and to all the other academics from UCD who've contributed, and to the staff here who've done a wonderful job in hosting us. It's been a pleasure to be here so far. Looking forward to tomorrow and Friday. So this is just day one. And also thank you to you. So the hardcore who stayed through the whole event. That's been great. And to those who've been joining us online as well. I know that these hybrid meetings are now the sort of de facto standard of how we conduct business. But it's been great to be part of this. And so to drum roll. Which way are we going to do this? Do you want to do first and then second, or second and first?
Go ahead.
Should do first and second. Go on then. So the winner of the poster prize is Geeta Singh from UCD.
Conferred in absence.
Unfortunately, Geeta's not here.
No.
Can I present you with the prize on behalf of Geeta? So there we go. Hey. So Geeta will receive a branded Chili's bottle. Let me just show you what you missed out on. So it's a lovely Cresset branded Chili's bottle, and a £50 €50 Amazon voucher.
Oh.
That's something. Thank you very much. I'm in the lab.
There you go.
Okay.
Right.
That's allowed.
That's a reasonable excuse,
Yeah,
I
that's
suppose. Well, Geeta, your Chili's bottle and certificate are there, and we'll be sending you a €50 Amazon gift voucher to enjoy.
So the second prize now goes to Marina Villacampa Fernandez from Padua Institute. Yeah, I can hand you. Thank you. So
Congratulations.
you don't get the bottle, okay?
But you do get a €25 Amazon gift voucher, which we will send you. Make sure Rachel has your contact details.
Okay.
And then we'll forward that along to you.
Well done.
Thank you. To be used, obviously, for science.
Yeah. I will check.
Well done. Thank you. And thank you to everybody who went to the effort of putting posters together. They were fantastic. So the quality of the posters was amazing. It was very difficult to judge that competition and sort of only present two winners. I wanted to give a prize to everybody. So that was amazing. Thank you for doing that. And it was great to see so much interaction going on sort of by the boards. Hey, here we go. That got you out of the lab.
You go with it.
Thank you so much.
There you go.
Thank you.
Congratulations. Well done.
Now last words from Morgan.
We can all stand here, it's fine. Three Stooges. Thanks everyone for joining today. I had a really good time. I hope you did as well. The analogy came up a few times through Cresset. You had a wonderful storyboard, by the way, throughout today, the sailor and the ship. So hopefully you can sail your own ship, as in your project, towards more computational applications in the future, right? We really are grateful that you came today. Thanks for making the event a huge success. I hope you enjoyed seeing all the posters. They really were of a great quality. And all of our speakers from Cresset in particular, can I just get a round of applause for Kev, Scott, Selma, Rob, of course, and Colin, Vicky, and Edith for joining us online as well. Thank you to everyone who chaired the sessions today. So for Brendan, Allison, Marina, really appreciate you stepping in today. So round of applause to you as well. As well as that, thanks to our Biorbirc staff who attended and really made the event a success. In your absence, we'll applaud for you. So Melanie Bauer, Sean Douglas, Kathy Keenan, and Jessica Chambers, thank you as well for all of your help, as well as all of the delegates from Crystal3. So Marcia, you're there in the audience, so we get to say thank you to you as well for everything you did, and Yolanda as well as a project coordinator for Crystal Cubed. In addition to that, I think we have all of our representatives from the UCD School of Chemistry. So Paul, obviously my PI, helped a great deal, as well as Marcus in both the venue management, but also with the finances for this event. So in that, on that note, to those of you who are attending online, enjoy the silence as we log off now. To those of you who are attending in person, enjoy the wine as we go to the wine reception. Thank you very much for joining us today. It's been a huge pleasure to coordinate this event for you, and I really hope that you enjoyed the day. I look forward to seeing you all tomorrow. Those of you who are joining the workshops at 9 a.m. sharp, we'll see you in the ALE rooms in Science East, and we'll sort out any issues you have with downloading the software. And beyond that, or I suppose just for the posters, if everyone could get them down for about 7 p.m. today, those who came